Slope fields are a good way to visualize what a differential equation is doing, and a good way to sketch some solutions to that differential equation. The idea of a slope field starts with a differential equation that's formed like this. It is an ordinary differential equation. It is first order, which means that I have one derivative of my unknown function y, and it's an ordinary differential equation, which means my y only depends on x. So it is ordinary differential equation, which means the unknown function y is equal to y of x, only one independent variable, and that's x, and it is first order. That means only one derivative of y. Okay, so slope fields can be drawn for ordinary differential equations that are first order. Now, how do you do it? Well, essentially what you do is you draw a diagram in the plane, in x and y, with a teeny little bit of curve that is tangent to the y, little slope at each x and y based on what f is. So you imagine that what f is describing is this describes the slope of y at x. But you don't know what y is. Okay, don't let that bother you. Just say it's the slope at the point xy. If you remember that, you're perfectly fine, and you can start sketching away. So let's do one. So let's look at this one here, where I have x squared times y. So y prime is equal to x squared times y. So how do you draw that? How do you draw the slope field? Well, what you do is you start picking some points. So I like to find out first, where is the slope equal to 0? Well, the slope is equal to 0 if y is equal to 0. So that's all along the x-axis, so I'll draw that in. Y is equal to 0, I get a 0 slope. Or if x squared is equal to 0, of course that means if x is equal to 0. And what I'm drawing is I'm drawing little hash marks, but they're actually little pieces of curve with the right slope. Y prime equals 0 means flat, horizontal slope. And so that's why I've drawn them that way. Okay, great. What about some other slopes? Well, it's good to try to divide up your domain to see what's going on where. So here we have x greater than 0, y greater than 0. Here I have x less than 0, y greater than 0. Here I have x less than 0, y less than 0. And x less than 0, x greater than 0, y less than 0. Okay, now, given that those pieces of information, I can tell you what the sign of y prime is. The sign of y prime in this first quadrant is positive. The sign of y prime in this second quadrant is also positive. Why? Because x squared is a positive number, so is y. Now, down here, I have x squared, that's still positive, times a negative, so that is negative. And here I have, again, x squared being positive times y being negative. Okay. All right. So given that information, I know that my little slope hash marks here are going to be going up, something like that. So a typical hash mark is going to go up. Here, a typical one is going to go up, here down, and here down. Okay, now I want to set things up so that I get the right kind of behavior. Well, if I look at the way that I move, if I'm going up in y for some particular x, my slopes will increase. They will increase as I move up. So they're kind of flat here and steeper as I go up. Additionally, as I move away from the y-axis, my slopes increase as well. So these guys will be somewhat steeper. So I guess maybe I should draw these steeper yet. And the same kind of behavior happens here. Get a little less steep as I get closer to the y-axis, and get a little less steep as I get down here. So things are very, very not steep near the origin. The same kind of picture happens on the other side. I get steeper as I move away from the y-axis. I get steeper as I move this way. And you end up seeing something that looks a bit like some hairs. And the idea is that you can kind of feel your way and flow around. You can feel your way through this. So, for instance, if I start here at a solution, let me give you an initial condition. So what this red dot is this is an initial condition. It's specifying a solution through this point. Okay, so if I start tracing that solution, the name of the game is you want to draw a curve that's tangent to each of these little slope lines that you've drawn. So that's one potential solution. Let me draw you another solution. This other solution maybe starts here, and it kind of goes down, and something like that. So here's another solution. One thing you'll notice is that there's a solution that goes right through the middle. The solution that doesn't change, the y equals 0. If you ever have a constant as a solution, that's called an equilibrium. So just as a definition, a solution to y prime is equal to f of x y with y equals constant is called an equilibrium. And equilibrium solutions come in stable and unstable variants. This one is unstable. It's unstable because my solutions go away from it. You'll notice if you draw any other solution nearby, they go away. This is unstable. If, on the other hand, the solutions were to get closer and closer to it, then it would be stable. And there's also the situation where solutions come in on one side and go in on the other. That's still unstable. So let me show you the three pictures here. Stable, unstable, unstable. And the thing to notice with stable and unstable equilibria, I'm going to draw my equilibria all the same for three different notional differential equations. The unstable ones go away. You could have one that comes in and away, that's unstable, but here's one which is stable. The solutions tend to get squeezed in. So all your solutions kind of come in. Here your solutions, not all of your solutions come in, and here all your solutions go away. Sometimes people will call this semi-stable. But it's still unstable. Okay, so that's kind of the way you draw these by hand, you can also draw them by computer. And here is an example in which I've drawn by computer the slope field for some differential equation. I'm not telling you what differential equation it is, but that's okay. Now let's find the equilibrium. There's one equilibrium. This equilibrium at 0 is unstable. You'll notice the little arrows point away from it. And here's another. This one is stable, and you can see the solutions point to it. And there's actually three kinds of solutions that are not equilibrium. There's the ones that start above the top equilibrium and come down. There's the ones that start below the bottom equilibrium and go away. And then there's the ones in between that switch from one equilibrium to the other. Those ones in the middle are sometimes called heteroclines. Now, with slope fields, you might say, that's all well and good. What are these things useful for? Well, let me show you a really nice example to close this out. So here is a slope field of all of the ocean winds on the planet. And you can imagine, just by following tangent to each of those arrows, you can feel how the wind is moving around in different places. You can see that there's two cyclones forming in the South Atlantic there. And you can see the circulation around South America and whatnot. So these slope fields are actually pretty useful. They're a great visualization tool. And let me tell you something. The simulation of wind moving around the Earth is actually a differential equation that's really hard to solve. So hard to solve that the Navier-Stokes equations that describe fluid flow in general, we still don't actually know if they always have solutions. We think they do, but we're not entirely sure. It's a really, really hard problem. Simulating it requires supercomputers. So slope fields are almost our best option, and they give you a really nice visualization. It's very easy to interpret. So go off and draw some slope fields.